Thanks. This is joint work with Richard Cole, Vasilis, Gkatzelis, who's here, Kamal, Jain, Tung, Vijay, Vazirani, and Sadra, Yazdanbod. So I'm going to talk about Nash social welfare and its relation to Fisher markets via convex program duality. So this is about fair resource allocation. So suppose you have n agents and m indivisible items, and you want to assign these items to agents. The agents have additive utilities. Okay. How do you assign it? That's the question. So one way to assign it is to say, let's be efficient, let's maximize the total utility of all the agents. And this is what this thing does. So it doesn't seem fair. Another extreme is to say, I want to be egalitarian, I want to maximize the minimum utility across all agents. And this is what this does. And this also seems a little bit extreme, that this agent is getting all these items and this guy is getting just one. Okay? The third option is what I'm going to talk about, Nash social welfare. This is assign it such that you maximize the product of the agent utilities. Okay? Now, any guess as to what this is going to do? This is what it does. It seems the right thing to do. Of course, I picked the example. But the takeaway is the Nash social welfare, it seems to balance between fairness and efficiency. It seems to find the right thing to do, right balance between these two. So for instance, one nice property it has is the scale freeness. It doesn't, because different agents might have kind of different sense of different proportion, the scale doesn't matter. So you can multiply all the values of one agent by a number, and that doesn't change anything. It doesn't change what the allocation is. Okay? And it has many other interesting properties that I'm not going to go into the details. That's not the point of the talk. I just want to say this is a reasonable thing to do in many settings. And one kind of evidence is similar notions have come up in many different contexts. Just listed 3 contexts here. So that is one indication of why it may be a nice thing to do. Okay. So this is what we want to do. We want to find an allocation that maximizes this product of the Nash social welfare. This is, as you might guess, an NP-hard problem because we are dealing with indivisible utilities. So what we want to do is we want to find an approximation. We want to find an allocation that approximates the best social welfare. So in particular, we're going to take the geometric mean instead of the product. Again, just a normalization. And we want the allocation to have this geometric mean not too far from the optimal allocation, so multiplicative factor of rho. Okay. So there has been a series of recent works considering this problem. Initially there was this order m approximation, and this was improved to this constant factor by Cole and Gkatzelis in 15. And in particular, it's not just NP hard, it's also APX hard. So this was shown also very recently. Okay, so let me say a little bit more about how this is done before I come to what we do. So natural thing to do is to write an integer program for this and take the fractional relaxation. Right? This is what we do always when we do approximation algorithms. And for this problem, it turns out that there is an integer program whose fraction relaxation is well known. It's called the Eisenberg-Gale program. So what I've done here is I've taken the log of this product and I've dropped this average. Right? So it's the same thing for, it doesn't matter, any monotone transformation preserves the optimality. So I want to maximize this sum of logs of the utilities, and this is just saying each item can be allocated to at most one agent, and this is just capturing the utilities of the agents. And it's an integer program because these are indivisible items, so an item is either allocated to an agent or not. And the fractional relaxation just allows these allocation variables to take on fractional values. Okay. But unfortunately, the integrality gap of this program is bounded, is unbounded. So the objective value of a fractional solution could be much, much smaller than the objective value of the integral solution. So your standard kind of rounding type approaches are hopeless. Okay? So before we go further, what exactly is this fractional relaxation and what is this Eisenberg-Gale program doing? This is very well studied because this fractional relaxation is solving this market equilibrium problem. So again here we have items and agents, and now the items are divisible because remember this is the fractional relaxation, and the agents have linear utilities, but we have now a market interpretation. So we assume that each agent has a budget of 1, and given you want to find prices to items such that when every agent buys his optimal choice, optimal bundle subject to budget constraint, the market clears. Demand is exactly equal to supply. Okay, this is called a Fisher market with linear utilities, and this has been well studied. And this is exactly what the fractional relaxation is computing. So if you solve this convex program now with the fractional relaxation, this xij, the allocation variables, will give you equilibrium allocation, and the dual or the Lagrangian multipliers for this supply constraints will give you the equilibrium prices. So this is well known. So the way Cole and Gkatzelis solve this problem is very non-standard. They define a variant of this market called spending restricted outcomes, and this has many interesting properties. So first of all, they show that there is an algorithm to compute this. It's a, they extend this combinatorial algorithm to compute equilibria, to also compute these spending restricted outcomes. And using this, they show an upper bound on the optimal Nash social welfare. Okay, I'll talk more about this now in a little bit. And also, the equilibrium allocation gives you a way to actually find an integral allocation, and they show that this way of doing it is actually, you can prove this 2.88 whatever approximation using this upper bound. Okay. So what is this spending restricted outcome? It's the same market equilibrium concept, but they say that no item can have more than $1 spent on it. Okay, so for instance, this is not an equilibrium because here the money spent on this item is $3. So it's violating the spending restriction, and this is the outcome for this instance. Here the prices can be more than 1, but the spend can be not more than 1. So if the price is less than 1, then the spend will be equal to the price. That's what it means to clear the market. But if the price is greater than 1, then it's okay for the spend to be equal to 1. Okay, so that's the variant. And they show this particular upper bound. So that what the upper bound does is, first of all, it scales the values in a certain way. Okay, let's not go into how it is scaled. And it looks at all the equilibrium prices, okay, that have price more than 1. So it ignores all the prices that are less than 1 and only looks at the prices that are more than 1 and takes a product. It shows that this is actually an upper bound given the right scaling of the values. Okay, so it works, it's magic. A priori it's not clear why this should be an upper bound for the Nash social welfare, why the spending restriction has anything to do with Nash social welfare. It's not at all clear, but somehow magically it works, and also the allocation gives you some information about how to find the integral allocation. Okay, so the one main contribution of this paper is to kind of demystify this whole algorithm, this whole approach. What we show is we give a different integral convex program that also captures the optimal Nash social welfare. Now, when you consider the fractional relaxation of this program, then that captures exactly, the fractional relaxation also captures the market equilibrium, but you can add a constraint that captures the spending restricted equilibrium. Okay, so this makes it easy to kind of compute this spending restricted equilibrium. It's just a convex program, you solve it, and that's it. Right? And the objective of this fractional relaxation is exactly this upper bound, this weird upper bound that I showed you. So in short, this puts the whole approach in the usual kind of rounding framework. So you write a program, integer program, you relax it, and then you round, right? And then this rounding also implies an upper bound on the integrality gap of this relaxation. And so we also have other things, other contributions I'll talk about, but this is the main thing. So what is this alternate convex program? It's related to this. This is called the Schmirev's convex program. This also captures the market equilibrium for Fisher with linear utilities. It's a strange convex program. So what is going on here is the variables are the spends. So Bij is how much agent I spends on item j. Okay, and it has this kind of strange objective function. These constraints are just, so this is in general, this is a budget constraint. You can have any budget for agent I, and this is your supply constraint. So Qj here is intended to be the price of equilibrium price of item j. Okay, so this thing in black captures the Fisher market with linear utilities, the equilibrium spend. So once you know the spend and this is a price, you can read off the allocation also. So now to this, if you add this constraint, Qj less than equal to 1, this captures the spending restricted outcome. So here the interpretation changes a little bit. Here the interpretation is Qj is the total spend on item j. Okay, so without this, the spend and the price are the same because of market clearing constraints, but now they're different. So now Qj is the total spend, and this captures the spending restricted outcome. And what more, now if you add these integral constraints, so these are not your standard 0-1 constraints. So these are constraints that says the spend on I that I spends on j should be either 0 or the total spend on j. You can see that this is the same as saying that j should be allocated to only one guy, right? So once you add these integral constraints, then you get as a solution to this the optimum Nash social welfare maximizing allocation. Okay? What more? So without this, just this thing with the Qj less than equal to 1, the fractional version, the objective value is exactly the upper bound that I just showed, where you take only the high prices. Okay? So why is this? What is happening? Why is this capturing the Nash social welfare? What does this have to do with Nash social welfare? Right? So what is an integral allocation? Integral allocation is, I started at 3 and it's 3:13. So, okay, yeah. So integral allocation is you allocate a set of items, you decide who gets what. Okay, so Si is a set of items allocated to I, and so this is an integral constraint. So you set Bij to be equal to Qj as long as j is in Si. So once you do this, once you fix this, you fix these constraints, and then you say, okay, what maximizes this objective function given this, right? So what this does is now it separates out this optimization into a separate program for each agent, and this looks like KL divergence between two distributions, if you know what that is. Okay, and what we know from that is the solution for that is basically the two distributions KL divergence is minimized, here it's maximizing, so it's negative when they coincide. So what the outcome of this is basically that the Bij should be proportional to Vij. Okay. And you use that and you plug in this and you do some reduction and you get that the optimum objective value is log of the utility. Okay, so then this is a separate one for each agent, and then so the total optimum, the objective is just the sum of the logs. Okay, so that is why this is capturing, this objective function is capturing the Nash social welfare. And here's the reason why the fractional version captures the upper bound. So again, it's the same idea. You can translate equilibrium allocation and prices to the spend, and you set the spend to be the minimum of 1 and the price, right? This is what you want, and you normalize it in a certain way. And so what happens is when you plug in these values, you reduce it, so you get something like this. You get something like Qj log Pj by Qj. So what is going on? When the price is smaller than 1, then Pj and Qj are the same. So this disappears, it becomes 0. And when the price is bigger than 1, Qj is equal to 1, so you just get log Pj. And that is why you get only the terms whose prices are bigger than 1 and you get the log, so this is like the product. So this says why we get this product of the prices bigger than 1, how you get that from here. Okay, so I've shown you why the integral optimum captures the Nash welfare maximizing 1, and the fractional optimum gives you the upper bound. And so this is also easy, just believe me, it is easy. So what do we, so these are all the 3 things I promise you, initially that this is what we do. So this explains their approach, it puts them in the standard kind of rounding approach. We also improve the approximation ratio. So this is the same algorithm but a more careful analysis. So earlier it was 2.88 something, but now we can improve it to 2. We also have other things we show. So for instance, there was this Eisenberg-Gale program that we knew for a long time. This was found in the 60s. And Shmirev came up with this program in 2010 or something like that. And it's like, okay, it came out of nowhere. What is the relation between these 2 programs? Here's the relationship. So here's the Eisenberg-Gale program, and here's the dual of the Eisenberg-Gale program. This is the Shmirev's program, and this is the dual of the Shmirev's program. And once you look at the duals, you realize that these are the same programs up to a change of variables. So here you take the log of these things, and you get these variables. So you just do a change of variables by taking logs, and then it's the same program. So this is how these 2 are related. If you just look at the primals, it's not at all clear how they're related. But if you look at the duals, it becomes clear how they're related. So more generally, we give a shortcut for taking duals of convex programs. So this is nothing new. It's a usual, take the Lagrangian and do all the usual things. But if the convex program has a certain structure, in particular if it has a convex objective but linear constraints, then we give a shortcut to take the dual. This looks almost like taking LP dual. So if you know how to write an LP dual, then you can do this. So I'm not going to go into the detail of this in the interest of time, but this is a very useful tool to know. So I encourage you to take a look at this and use this thing. And this also gives us new convex programs. So for instance, if you have quasi-linear utilities, this means you have utility for money. Then earlier it was not known how to write a convex program for that, but using this technique, it makes it very easy to find these convex programs. So we have more things. So for instance, for this particular algorithm, we said, we improved the upper bound from 2.88 to 2, and this is tight. We show an example where this is how much you get. We also show a lower bound on the integrality gap, that is 1.44. We define a new market model called utility restricted markets. This is the counterpart. Instead of restricting the spend, you restrict the utility, and we find equilibrium of this. We show rationality of equilibria. We have several extensions. So there's a lot in this paper. I encourage you to take a look at this. So that's it. Thanks.